Okay. Sound is okay in the back? Yeah. Great. Yeah. Okay, hello and welcome everyone. I'm Magnus Larsson. I'm from Calista Enterprise, a consultancy company based in Sweden. And in this presentation, I would like to share some experiences from using different types of discovery services that I've been experienced while helping customers to start getting and develop and deploy microservices. A few words about me. I've been using Java since first release. I've been helping customers to design and implement distributed systems for the last 10 years. Something that I find very, very hard and tricky, specifically in terms of robustness, resilience, and scalability. Fortunately, during the last years, as I assume you all know, there have been tools released, open source-based tools, that at least technically makes this a bit easier. Netflix OSS, Spring Cloud, and Docker. So for the 2 or 3 last years, I've been helping customers to understand how to apply a microservice architecture within their existing system landscapes. And for me, microservices is basically just an architectural style of how to use a distributed system. So all challenges that applies to distributed systems also applies to microservices. And when I have some free time, whenever I can, I try to exercise some cross-country skiing. I really enjoy that. This presentation actually had its starting point when I gave another presentation 1.5 years ago on our own conference, Calista Developer Conference, where I gave an introduction to how to develop microservices based on Spring Cloud, Netflix OSS, and run them on Docker. So you see the usual suspects here, edge server, discovery server, config server, and things like that. At the same conference, a colleague of mine presented Kubernetes as a container orchestrator and cluster manager for containers. And after this conference, I had one question in my head. Well, what happens if we try to combine these two tool sets? What happens if we try to deploy microservices developed on Spring Cloud, Netflix OSS on a runtime environment based on Kubernetes? And to understand that a bit better, I started to write down all the main capabilities of the two alternatives. So you can see on the left capabilities that you get from Spring Cloud, Netflix OSS, and to the right, you see typical capabilities that you get from a container orchestrator. So you have cluster management, declaration of desired state, and things like self-healing, rolling upgrades, and automated scaling. So if you do just at the first glance, they seem to complement each other rather well. But there is one area of conflict, and it is around service discovery, since service discovery is typically built into a container orchestrator such as Kubernetes. What this means practically is it should be very weird to deploy Netflix Eureka as a service discovery mechanism on top of Kubernetes. That would not make any sense. And as it happened, a short time after I did this presentation, I was engaged in a customer project where we actually got into exactly this situation. So we had developed a set of microservices based on Spring Cloud and Netflix OSS. And then it was decided to deploy them onto Kubernetes for production. And as it turned out, we could reuse all features except for Netflix Eureka. We replaced that with a discovery server built into Kubernetes. And to be able to do that, we had to change some code in our microservices. And I didn't feel that was the right way to do. We must have missed something when we were forced to change our code just because that we changed discovery service. And at the same time, I had discussions with a few other customers. First, regarding the fact that there are other container orchestrators available. And what happens if a customer starts with one container orchestrator and then decides to change to another? How will that affect the code? Can we move our microservices without code changes? Can we avoid vendor lock-in, so to say? And another question that I had with more cautious customers were that they for sure wanted to split the monoliths in smaller components, microservices if you want, and they want to Dockerize them and make them run as containers, and they want to take at least parts of them into the cloud, but they didn't want to do it in one step. They wanted to be able to do it step by step. So again, the question came up, can we develop microservices in a way so that we can initially run them without containers and then move them into a container world without changing code in the microservices? And that was exactly the case that we failed on in the customer project I just referred to. So all these questions together, using them, I formed a kind of a personal quest last year to really get into and understand what it takes to write microservices that can be freely moved around and deployed and be running without containers. And when I deploy them into containers, be able to deploy them into various container orchestrators without being forced to rewrite code. And based on interest from the customers I talked to, I selected these 4 alternatives. First, without containers, and then using Netflix Eureka as a discovery service. And then I selected the 3 container orchestrators. You can see Kubernetes from Google, Docker in swarm mode, and Amazon's EC2 container services. So for the rest of the presentation, I would simply like to go through the various alternatives and see how a demo application runs on the 4 alternatives, and then wrap up with a little demo of how this affects the code and how the configuration looks. Okay? Yeah, I can reveal that. I guess it will not be a cliffhanger anyhow. The most challenging part to be able to do this was to really understand how the different platforms' discovery mechanism works, so you can find a good abstraction when you write your code. So what is service discovery about, really? To me, it's two main things. We are in a landscape with many moving small parts. Instances of microservices comes and goes. And it's the most important feature for a discovery service is to keep track of what instances we have available in the network for each type of microservice. Keep track of the IP addresses and ports to help a client to understand where to place its request. But also it's very important to understand the health state of each instance. Are they available? Are they ready to receive a request? There can be many reasons why a microservice instance can be available but not ready to actually receive a request. It can be going through an update. There can be some temporary failures. It might be into a starting phase that takes a couple of seconds to complete. If you start a microservice based on Spring Cloud and Spring Boot, you know it can take for sure a few seconds before it starts up and is actually ready to receive requests. Okay, so first out, running without containers using Netflix Eureka as a discovery service. And then it looks something similar to this. Each instance, when it starts up, gets in contact with one of the discovery servers and registers, and then at the regular time interval, it tells the discovery server that I'm still here and okay. And clients can use a library from Netflix called Ribbon that offloads them with all the mechanics. So it is in continuous contact with Eureka to understand what instances are available, and it can offload the client to do requests to a proper instance using a proper load balancing mechanism, such as round robin. So let's try it out. I have a minimalistic demo landscape. I have a quote service which exposes an API for receiving quotes. And I have a very simple web portal where a user using a web browser can consume these quotes. So I'll start up 2 quote services, 1 portal instance, and then 2 discovery servers, 2 Eureka instances. And I'll do it without Docker. Yeah. Let's forget about that window. So I'm using a small utility program to start up the 5 microservices instances. They are all based on Spring Boot and Spring Cloud, so they are Java applications, basically. So you can see the output in here, the discovery services, for the quote services, and for the portal. This is just applicable for development and test, of course. But after a while, I should be able to get in contact with one of the discovery services. Yes, here it is. Oops. Can you read it? So here we can see that the system landscape has got started and the different components have found each other. So you can see that the discovery server can see it's the other discovery services. It can see the portal and the two quote services. So the demo landscape is there. Now we can try out the portal. Yeah. And we can ask for a couple of quotes here. The most important thing is not the quotes themselves. The most important thing is the IP address here. That is the IP address of the quote service that actually responded to the request. So here we can see that we get responses from different ports, meaning different instances. And I can also start a continuous flow of sending requests here. And it's the one on the top that is the last. So what I can do now is to be a bit bad. I can stop one of the quote services. And what you see here is that the user experience is not affected, so we have a robustness. It will now only take requests from 8082, so 8081 is gone. And if we look at the discovery server, the quote service is unregistered from this discovery service. So we can clearly see that we have good robustness in this case. I can do much more, but I have other demos that I want to go through, so I'll simply stop this now. Okay, next, the container world. But before we go into orchestrators, I will just talk a few minutes about plain containers, simple Docker engine. And a year ago in Docker 1.10, it came a fully fledged DNS server built into the engine, meaning that when containers were started and stopped, they were registered and unregistered in the built-in DNS server. So they could be looked up by their name. And you might think that, isn't this everything I need? A continuously updated DNS server, and as a client, I can talk to the DNS server and get a list of IP addresses. So you could, for example, set up this demo landscape using plain Docker Compose, like this. And then you can do Docker Compose up, and you can scale up your quote services to 2 instances with the Docker Compose scale command. And then you can jump into the portal container and ask the DNS server for what IP addresses the portal can see of the quote services. And if you try that, you will actually get 2 IP addresses back from the DNS server within the scope of the portal. So this seems terrific. What's the problem? The problem is if you try to use it. Then you only will get responses back from one of the 2 instances. That's not good. So what happened? What happened with the round robin? That's a fluffy robin, by the way. You can call it round. What happened with the round robin? As it turns out, DNS clients have for a very long time been coded in a way that they will only use one IP address if they get a list of IP addresses when they translate the DNS name. And even worse, they tend to cache this information for a very long time, and that's not very applicable in a landscape where instances comes and goes. And thirdly, there is no mechanism of health state checking within a DNS server environment. So even if you have a number of IP addresses, you have no clue if they are stale or if they are actually useful. So even though Docker Engine and Docker Compose is fantastic to use for development and setting up test landscapes, it's not to be used in production. You need something more. You need a container orchestrator. First out, Docker in swarm mode. Docker, it came with Docker 1.12, released late July last year. And it's a fully fledged cluster manager for containers. So you have a set of master nodes that runs the orchestrators, and you have a set of worker nodes where the orchestrator schedules containers. Starts them, monitors them, and stops them if they are not at a good health state. And most important, there is a abstract service concept in Docker in swarm mode. So you can create a service, and when that service is created, a static IP address will be allocated that is available throughout the swarm cluster. And that IP address will never change. It will be the same for the lifetime of the service. And that's very important because that is the way you avoid the DNS problems I just talked about. And there is a load balancer in each node that Swarms provides that will take the request on if someone calls that IP address. And it is continuously updated by the orchestrator with the actual available instances of containers for that service. So it can forward the request to a healthy container. That is how the discovery is resolved internally inside the cluster. And to make the services available outside, externally, for external clients, there is something called a routing mesh. So when you create a service, you can tell the orchestrator to export one of its ports outside on a port that is available externally outside of the cluster. And it will be made available of every node, on each node in the cluster. So that way, whatever node the request receives from outside, it will be routed to the abstract service concept, and then it will forward the request to a proper container instance. So that is the way service discovery is handled in Docker in swarm mode. So to demonstrate this, I have set up a minimalistic swarm cluster, 3 nodes in VirtualBox, and I have joined them with Docker Swarm commands, and I have deployed one service that's a visualizer, so you can visualize the state of the cluster. So you can see the 3 nodes, and you can barely see. I can see, so I tell you. Here is the visualizer container, the only container that runs for the visualizer service. So what we can do now to set up the demo on Docker in swarm mode is to first create an internal network that is available for our instances. And then we create a quote service, and we declare a desired state for the orchestrator. At all times, I want to have 3 instances up and running for this service. And then I create the portal, and there one instance is sufficient, I say. And then I export its port 9090 on the external port 9090, so it's available on all cluster nodes. Let's see what we have here. Is it possible to read from the back? Hardly. So I'll tell you what's happening here. So here I have the commands that you saw on the PowerPoint slide. So I'll just paste them in here. And you can see that the portal is scheduled on worker node 2, and then the 3 quote services are scheduled, one on each node. I could have been specific when I created the services, but I allowed the orchestrator to do it by default, and then it simply spread them out. Okay, so we can try to access a portal. It runs on worker 2. I don't care. I will use IP number. No, it's hard to see. I will use the IP address of the manager, just to be sure that I don't hit the node where it actually runs. So here it comes up again. Of course, it looks exactly the same as when we run without containers. Oh, I can start it like this. And we can see, hopefully you can see, that we get responses from different IP addresses, meaning different containers. 5, 6, 7. Okay, so what I can do now is to, I don't need to see that, is to kill one of the containers to see that we have resilience. So I kill the quote services running on the manager. That one I tried at least to kill. What happened? Let's kill it again. No, now it's of course not there. Now you see it's gone. So the scaler detects we only have 2, and we've been asked to have 3 up and running, so it starts the 3rd one again. And if we had a little better screen resolution, we could have seen that on the right side here, we could not see any problems by doing this. So we have a clear robustness, and after a while, the new started container comes back up again, so we have also the resilience that we want to. And I can actually kill a whole node. So I kill worker 1. So we can see we only have responses from 5 and 7. So 6 is gone, and you can see in the visualizer that the node is now red. It's gone. And after a few seconds, the scheduler detects this and reschedules the 3rd quote service on one of the 2 available nodes. Okay? So it seems fairly robust. I just started up here. Okay, over to Kubernetes. Kubernetes is a far more mature container orchestrator compared to Docker in swarm mode. But from an abstraction of a service discovery perspective, they actually works very similar. Things are named a bit different. The orchestrator is called the control plane. The load balancer is called the kube proxy. And the control plane has a helper on each worker node called the kubelet that manages the local instances. Otherwise, it's basically the same. When the service is created in Kubernetes, a static IP address is allocated that is allocated for the lifetime of the service. And you can export a port for a service outside that makes it available on the outside on every node in a cluster. One thing that you can do in Kubernetes that you can't do in Docker swarm mode that is important from a service discovery perspective is if there is available an external load balancer outside of Kubernetes that is aware of Kubernetes. Kubernetes can automatically provision the externalized port to the load balancer, meaning that the clients don't need to keep track of what IP addresses the cluster nodes are available on. They only need to know about the IP address of the load balancer. So being able to do that automatically is, of course, a very good thing. To demonstrate Kubernetes, I have now moved out to the cloud, and kind of natural to use the Google Cloud. That makes it very easy to set up a Kubernetes cluster. And while I'm in the cloud, I also would like to try out auto-scaling, besides the other tests I've done. So to set up a Kubernetes cluster in Google Cloud is very, very simple, actually. You just define a couple of environment variables. In what region do you want your cluster? How big machines do you want in the cluster? And you enable auto-scaling, and you say minimax for the auto-scaling. And then you run a simple script. And then you have 2 options. Either you take a very long coffee break or a very short lunch. But after that, you have your cluster up and running. And then you can use commands similar to the one with Docker Swarm to create your services. They look a bit different, but they do the same thing. The exception here is the type I specified for the deployment, where I ask Kubernetes to automatically provision the external ports into the Google Cloud load balancer, so you automatically get it available. It's very good, specifically in the case if you do auto-scaling. It's very hard for clients to know about the new IP addresses when new nodes comes up due to the auto-scaling. And the remaining thing I have to do is to enable auto-scaling also of the containers. They are called pods in the Kubernetes terminology, but the same thing. So then I have auto-scaling both for the nodes and for containers. This unfortunately takes a couple of minutes, specifically the provisioning to the external load balancers. So I've already done it. It takes too long time during a presentation. But after that, we can ask for the services. We can see the pods, one container for the portal, one for the code services, and I can see the nodes in the cluster as I look right now. So then we can put some load. We can do all the tests that I did with Docker in Swarm mode, but it works the same, so I don't repeat them. What's interesting here to see what happens with the cluster if you put some load to it. So to put some load on it, I have not one web browser, I have 3 web browsers, so that the cloud really can feel the pressure to finally engage auto-scaling. What I can see here is it possible to read, or is the font too small? It's okay? What I can see here is the external IP address of the portal service. And that is the IP address that I've used in the browsers. So I hit the Google Cloud load balancer, and that it will forward the request into the Kubernetes cluster. Here I can see the available nodes, the available pods, and up here I can see the current workload. Did I not? No, they are running. So here I can see the load that Kubernetes sees on our cluster. And when it goes over 50%, it's expected to start up new pods. Now it stays at 45%. That was bad. At all other times I've done this demo, this has been fully sufficient. No, they are all running. Why is it? That's very strange. So normally this percentage figure goes up to several 100%, and then it responds by launching. Okay, thank you. So now the load is at 900%, and it's about 50%. So the Kubernetes cluster has automated scaled up new containers for the code service. That's quite neat. And if we wait a little bit further, it will also start up new nodes in the cluster. To not kill my credit card, I will now stop this because it's a bit expensive. So if we, this is actually what we just saw. And if we wait a little bit further, we will actually see Kubernetes starting up new nodes as well. Finally, Amazon EC2 container services. First, I have to say, up until August last year, I didn't find this orchestrator very useful in the case where you have a number of microservices that are cooperating, that need to communicate with each other. And that was due to the load balancer that was available at that time, the elastic load balancer. It's far too static in its mechanics to be useful. And it's also very, very expensive to use in a scenario like this. But in August last year, this was changed when Amazon released an extension on top of the elastic load balancer called an application load balancer that have exactly the characteristics required to be able to manage a landscape of many moving small parts, containers that comes and goes. The landscape looks a little bit like this. Again, from a service discovery perspective. There are much more to say, but again, from a service discovery perspective. So there is an orchestrator running inside Amazon. We are now no longer talking about open source, so we have no clue of how it actually looks, but somewhere there is orchestrator running that orchestrates a number of EC2 instances, and on each EC2 instance runs a local Amazon ECS container agent handling the containers running on that EC2 instance. And then the load balancer part is moved out of the worker nodes, and it runs on top of the Elastic Load Balancer, but called an application load balancer. And to try it out, I set up a ECS cluster together with an application load balancer, and then I enabled, again, auto-scaling of nodes and auto-scaling of containers. They are called tasks in Amazon, but otherwise it's the same. Setting up this is far more involved compared to setting up a Kubernetes cluster on Google Cloud, so I just give a short summary here what needs to be done. You first create the container services cluster, and then you need to enable an auto-scaling group. That's the same auto-scaling group that you're used to if you set it up for EC2 instances. And then you have to enable auto-scaling of the tasks, so you can auto-scale containers. And finally, you have to configure the application load balancer. And it works a bit different from the other load balancers that we have seen for Kubernetes and Docker in swarm mode, in that it does its load balancing based on the incoming URL. So it's a URL path-based routing. So it works similar to an edge server such as Netflix Zool, if you have looked into that. And I don't go into any details besides the application load balancer. I just want to show how its configuration looks like. That is totally impossible to see. See if I can, no. Yeah, oh. So here we can see that any request that comes into API quote something is routed to the load balancer, to the quote services, one of the quote services. And any other non-API related request, these three, they are routed to the portal service. And then you can continue like that. Oh, that was interesting. And we can do the same test again. I'll just demonstrate that the demo works in the Amazon environment. But don't repeat all the tests. But here you can see a URL that obviously goes to Amazon. And in the front of the long URL, you can see ML, that's me, and application load balancer. So it hits my application load balancer. Yeah, so we can see that we get requests done through the demo application when it runs on Amazon as well. How am I doing time-wise? How much time do we have left? 15 minutes. Yeah, should be okay. So now we have seen all four environments and how our demo application works, and I've told you a bit of how the discovery mechanism works in the different environments. I would just like to wrap up saying a few words about the programming model, so show some code and configuration. I've chosen to do this using Java and Spring Cloud because I like it a lot, and it makes it very easy. But there is nothing conceptually that stops you from doing this in any language. We're using any framework, actually. It's just very easy to do it using Java and Spring Cloud. The three container orchestration tools have an abstraction of a service concept. They work a bit different, but there is an abstraction that you can use for your programming model. When it comes to Eureka and Ribbon for Netflix, they don't have this concept at all, so they're totally different. Thanks to Spring Cloud, you actually can have an abstraction of a service concept. So they become, in the end, rather similar. And then I would like to bring forward the actuator in Spring Boot. It comes with a very good health endpoint that you can customize if you want to. But it's very useful for setting up liveness and readiness probes in the different for the different discovery mechanisms for the orchestrators. It's very useful to make that simple. So here is some code fragment. It's actually from the portal service that needs to consume requests and send away requests. It's a standard Spring Boot application, and it declares a REST template to doing outgoing requests, and then it has a standard Spring MVC controller to take requests from the web browser, and then it uses the REST template to do the outgoing call here. And to make this code work in all these 4 environments, all I had to do from a programming perspective was to add these 2 annotations. And the meaning of them are that the first annotation enables us to use a local discovery service such as Eureka if we want to. It doesn't enforce it, but it allows us to do it. And the load balanced annotation on the REST template bean will inject Netflix ribbon under the hood of the REST template. So anyone that uses the REST template will go through Netflix ribbon without knowing it, without needing to care about it. But what's important to understand here is that now when we have injected ribbon under the hood of the REST template, this is no longer a DNS name. Instead, it is a logical name resolved by ribbon. But there we can affect ribbon by configuration, so it resolves it differently depending on the environment we run our microservices in. So that is kind of key to us. Okay? But that's basically all the code in the end that I needed to add. And here is some configuration now. I'm using Spring profiles, so different profile for different environments. And first I use on the top the default profile for the container orchestrators, and there I of course switch off use of Eureka, and I translate the logical name code service to code service :8080 because that is the internal name within the clusters where you can reach the code service on. At least for Docker in Swarm mode and Kubernetes. When it comes to Amazon EC2 container services, I have to go through the application load balancer. So therefore, I have a specific profile for Amazon where I override the naming in the default profile. And so I add this very long DNS name for the application load balancer. And finally, and thirdly, I have a profile set up for use of Eureka as a discovery server without containers. And then I, of course, enable use of Eureka, and I also add a property here where I specify where my microservices can find the discovery services. And for high availability reasons, of course, I have always more than one discovery service available. If you want to know more about this, we have a blog series where we write various posts regarding how to develop microservices using Spring Cloud and Netflix OSS and Docker. We have 2 tracks. Again, it's very hard to read, but you can try the URL there. We have one track for how to develop microservices based on Java, and we have one track for developing microservices based on Golang. And in the Golang case, very important to understand that the microservices are written in Go, but they will communicate with the services provided by Spring Cloud. Config server, edge server, security server, discovery server if you want to, and so on. It's quite interesting. Time to summarize. I find that I accomplished my mission. I found a way, rather simple actually, once I clearly understood how the different discovery servers worked in the different environments. To be able to write my microservices that I didn't have to change the code while deploying to the different platforms. I only had to apply different configuration. And I clearly avoided vendor lock-in. That's basically the most important criteria. But at the same time, I could use platform-specific characteristics such as auto-scaling in the cloud for Kubernetes and Amazon. And again, I really want to emphasize that I did it in Java. I don't have to. I can do it in any language. I guess I have 2 minutes for an extra demo, just to emphasize this statement. What I did actually recently was that I read through the Google, no, back again. Where is it? There it is. I read through the blog series about how to develop Go-based microservices. So I re-implemented my Java-based code services in Go. So now I would like to demonstrate how I can do a rolling upgrade of my Java-based code service into Go. And when doing that, I will ensure that the user experience is not affected by my rolling upgrade, replacing Java with Go. So it will run here. And then I take this command. It basically says update the image to a Docker image based on Go. I can specify a lot of. No, I should have had this up and running. So what's happening here is the Java version is taken down one by one, and the Go-based is started up instead. And if everything seems to work fine, it continues with all the 3 instances. So it works very fast because I've not set any timing, and we have not seen any errors in the user experiences. The only thing we can see is that the quotes have changed a bit. They are all about Go now. And while I'm using Go, I can, of course, try to see if they start faster compared to the Spring Boot applications. So I can ask the orchestrator to ensure that I at all times have 10 instances instead of 3 instances up and running, okay? And now I have that. And in a few seconds, they all turn green. You see? Can be very useful in a landscape where you have a lot of Java-based microservices, but some of them really needs to respond quickly to an increased load, automatically or manually, so that you very, very fast can start up. And then it can be worth the effort of re-implementing those services in Go. You have to write a bit more code. You don't have the simplicity provided by Spring Cloud, but it can definitely be worth it for some parts of the microservices in your system landscape. With that, I'm done. Do we have a few minutes for questions? Yeah. Microsoft Azure? Yeah, the question was if I tried out Microsoft Azure. Yes, I have done that. It looks really good. And recently they have come up with Azure Container Services, where they say they have support for both Docker in swarm mode, Kubernetes, and Apache Mesos or DCOS. I'm really looking forward to look into that new service. I've not used that specific service, but it looks really interesting. Yeah. Yeah. Okay. 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 Maybe we can talk a bit after. We can share some experiences. Yeah. Any other? Yeah.
We're moving on platform onto AWS. What sort of thing would we need to consider, whether to just use the Amazon load balancer or whether to use something like Eureka instead?
In what platform?
It's just simple few microservices.
Yeah. And you will deploy them on?
It'll be on or deployed on Amazon. Would we just?
Yeah. Yeah.
What would make us consider Eureka instead of just using the Amazon load balancer?
I would use Eureka if I don't run my containers, don't run my microservices as containers.
But they're Spring Boot apps.
Yeah, Spring Boot's apps, but you can run them directly onto EC2 instances if you want to. And then you need some discovery service that is not coming with the Docker container runtimes.
Right.
And
so
then
you need a Eureka to be able to.
You need something similar to Eureka, but I guess that you could, I don't know how useful the application load balancer for Amazon will be in that case.
Right.
I'm a bit unsure of that. I've only investigated it from a perspective of running my microservices as containers in Amazon Container Services. Oh, long answer. So I would definitely look into their application load balancer first to see if it can route requests to something else than containers, because then you're home. But otherwise, I would definitely set up Eureka. Okay, or something similar. There are alternatives, but yeah. Any other questions? Okay, then I say thank you for attending.